Hey everybody, welcome back to video 4 in chapter 6 for physics 11. We are going to look at the conservation of energy again today. We're going to call this conservation of energy round 2. But before we get there, I actually have to finish off with the tail end of last video. I should have thrown this in, but the video just got too long, so I bump it to today, or this video. I need to show you guys something about efficiency. So when we look at energy transfers, energy changing from one type to another, here it says sometimes some energy is lost to heat during an energy transfer. That should probably say that almost all the time, to be honest. There is some energy that is lost to heat. There's some energy that ends up sort of being wasted or not converted into the type that we desired or wanted. So what I want to look at today is quickly, or to start with, how does efficiency work then? And what we're going to do for efficiency is we're going to say this. You've got a machine of some kind. And this machine, pretty much all machines, they're energy transfer machines. They're going to convert energy from one type to another. Now in Physics 11, all of the machines we look at are going to be electric. So they are going to have a plug on one end. So there's our little plug. And the energy that goes into the machine. So the energy that goes in is going to be from this equation every single time. E equals P times T, which I think shows up on your formula sheet in some other arrangement. It's like power equals energy over time, something like that. But I'm just sort of changing it up to solve for energy. So your energy in for these electric machines is always the power, the wattage, multiplied by how many seconds the thing runs for. Now, the job of this machine, of all machines, is to convert that electrical energy into some other kind of energy. Right? It's an energy transfer machine. So what this machine is going to do is it will convert into one of the three types of energy that we've looked at up to this point in this chapter. So this machine could take your electrical energy and it could lift something up into the air. It could convert into potential energy, which is mgh. And in a question, you'd look for keywords like lift. Right? You'd ask yourself, is something going up into the air? Or maybe this electric machine, maybe its job is to convert the electrical energy into kinetic energy. We've seen that. You'd want to look for keywords like it's making something move, or now something's going fast. And then the last type could be, I'm sitting here drinking a coffee while I'm making this video. We could be talking about heat energy. I used a kettle to heat some water up. So maybe we're taking electrical energy and we're using that to heat something. And that one should be pretty obvious. So that is your energy out. That's what you have to decide in a question, is which of those three types of energy is the machine giving us in the end. Now, what's going to happen? Like this little note says, some energy is going to be lost as heat. So this machine is going to get warm. So some of that electrical energy actually gets wasted, right? We don't really want the machine to get warm. That's just a byproduct of all machines. And that efficiency will come out as something less than 100%. So here's the equation for efficiency. It's pretty darn easy. Efficiency is equal to the useful energy that you get out. I don't want to just say energy out, because you do get all the energy out of the machine that you put in, just not in the useful form, which is the green stuff over here. It's the useful energy out divided by the energy that you put in, and then we convert into a percentage just by multiplying by 100. So that's always got to be less than 100%. In fact, here's kind of a crazy stat that might get you thinking and not make you feel so good, unfortunately. But when you fill up your car with gasoline, for those of you that are driving, you know that gasoline is expensive. A truck like I have an F-150, I can easily go and put $150 worth of fuel in that truck if it's near empty. And if I think about, I try not to do this, but if I think about the efficiency of that motor, so like a gasoline or even a diesel combustion engine, the efficiency is somewhere around 30%. So that means if I put $150 worth of fuel in my truck, the whole job, sorry, phone call from my family upstairs, the joys of working in the basement. I think I was saying that my truck and all vehicles are about 30% efficient. So that means I put $150 worth of, I guess, chemical energy into the truck through gasoline, and then the machine, the motor is going to convert it into kinetic energy. So if I multiply by 0.3, I get like $45 worth of actual kinetic energy of motion out of my truck. And then the other $105 was wasted as heat. I just heated up Penticton. And that's how it's going to go for like all cars. You get only like 30% of the money that you put into a gas tank. 30% of that goes to propelling you forwards, giving you kinetic energy, and the rest is just making your car hot, which is really too bad. But you got to just let that thought go and just grit your teeth and drive anyway, right? So there's the equation for efficiency. Let's try out an example. See if you can pick out one of the keywords to figure out whether we're looking at potential energy or kinetic energy or heat energy as the energy out, because that's really the only thing you have to figure out for these kind of questions. So let's try this one. Determine the efficiency of a 30.5 watt motor that lifts a 27.1 Newton load, 12.6 meters vertically in 18 seconds. Hopefully as you read that, you're looking and going, hey, I see a word that's going to help me. We are lifting something, and even vertically it says. So what kind of energy out are we talking about? Well, the energy out, we're lifting something, that's going to be potential energy, MGH. So if we go run the equation, the efficiency is going to be the MGH over the energy in. We said these things are electric, so it's always P times T. Now what's kind of cool here, and you might notice there's something that's done for us already. The load that it's lifting is 27.1 newtons. So you got to look at that and go, hey, I know what that is. 27.1 newtons, that's the weight. That's already M times G. That's done for us. It's not just a mass in kilograms. They've actually already gone ahead and multiplied by 9.8, which is kind of nice for us, but you do have to catch that. So if we go and we plug those numbers in, I've got the M times G done. That's 27.1. We're lifting 12.6 meters. And then we've got 30.5 watts running for 18 seconds. Be a little bit cautious. I'm not going to show the 100% until the end, if that's okay. Be a little bit cautious here with bed mass. When you go to type this into your calculator, again, I'm a broken record, right? If you're going to divide by 30.5 times 18, you're going to have to do that in brackets like I'm doing here. 30.5 times 18. You get that number, and then you can multiply by 100 to turn it into a percentage. Looks like we're at about 62.2% efficiency. What happened to the other 38-ish% of the electrical energy we put in? Well, it made that little electric motor warm, right? It got wasted as heat. So that's what efficiency calculations look like. You really just have to figure out that energy out piece, which I don't think is too bad. Okay, let's try. Oh yeah, here we go. The ultimate conservation of energy. I should probably put the quotes on ultimate. So we're going to revisit the conservation of energy equation that we saw last day, and we're going to add something in today. So MGH plus 1/2 MV squared equals, this is what we saw last time, MGH plus 1/2 MV squared. Conservation of energy, we're going to add something new for today, and that is work onto both sides. F times D. So that blue text is new. Here's what you want to ask yourself. We already sort of played this game, so I'm not going to go through too long. Maybe I'll just label the new ones if that's okay to save time. This MGH right here was, does the object start? Well, I'll put something. Does it start in the air? Slash on a building, slash on a hill. And the 1/2 mv squared was, does this thing start with some velocity? Is it moving initially? And now we've got this F times D term. And what we want to ask ourselves for this thought experiment is somebody pushing forwards? Do we have like a little helper? Somebody trying to add some energy. And because it's somebody pushing forwards and helping us and adding energy to the system, sometimes I will talk about this term and I'll call it elves. Do you have any elves? Right? Elves are like Santa's little helpers. Maybe they've gotten bored in the summertime and they've come down to Penticton and they're going to help us out with some physics. So there's the questions you want to ask yourself before something happens. And then after something happens, do you end up in the air? Been there, done that. Do you end up with velocity? Been there, done that. And now this F times D, we're going to say, not is there something pushing forwards, but is there something pushing backwards? Is there something pushing against you? And that pushing backwards, quite often for Physics 11, will be the force of friction. So if you see friction in a question, it's going to be that F right there, something pushing backwards. And you know this if you rub your hands together, that when you rub your hands, friction creates heat. So sometimes in physics, we'll call that term on the right-hand side work out, or you might hear it, somebody say, hey, is there any heat involved or heat created? That's from a force pushing backwards. So this is the ultimate energy of conservation equation. This is what we're going to work with from this point forwards. We're always going to put those F times D terms in there. Let's try a couple of examples so you can see what this looks like in practice. So, scenario 1, we are going to have somebody adding some energy or adding some work in. You can see here we've got an elf, we've got a helper, a pusher. So let's try this example. We want to find the final velocity of this car. It is moving already at 2 meters per second. It's 1,200 kilograms. And then Joe is going to come along and he's going to push with this force of 500 newtons for a distance of 6 meters. How fast is the car going at the end? So, ultimate conservation of energy. I want to list the whole equation and then go through and cancel out the stuff that we don't have. I promise again that that is easier than trying to just figure out what you do have. So I'd highly recommend take the few seconds, write the whole thing out, and then we can go cross out the stuff we don't need. So let's look at this. For this scenario, we're pushing the car. Does the car start in the air / on a building / on a hill? No, it does not. Does the car start with some velocity? Hey, we've got a VI, so yes, it does. And do we have an elf? Do we have a helper? And hey, let's give them some like elf shoes and elf ears. Maybe to have another ear sticking out. Hopefully those don't look like horns. Yes, we do. We have a helper. F times D. Somebody's pushing with the car, helping it out. Now, does Joe push the car up a hill, up onto a building, up into the air? No, it's always on the flat road. So we're not giving the car potential energy. But is it going to make the car go faster? Is this car going to have some velocity at the end? Yeah, it definitely is. And is there any mention of friction? So notice I changed up what I said there. There would be in real life friction in this question, but because the question doesn't say anything about it, we don't actually have to worry about friction pushing backwards. If I gave you a coefficient of friction or mentioned a force of friction, then you could put it in, but we're going to ignore friction. So we'll take that out. Now what we're left with is a 1/2 mv squared, so some kinetic energy, and then Joe pushes, which is going to give this car more kinetic energy. That makes sense. Last time we saw conservation of energy, we were able to cancel masses because it showed up in every term in the equation. Notice that is not the case anymore. We've got a mass in the 1/2 mv squared, but not in the work term. So you actually can't eliminate the mass of the car. We're going to have to keep it in there. From this point forward, it really is just number crunching. You just go to your calculator. Remember I mentioned that people forget to square velocities all the time, so catch that when you're doing the 1/2 mv squared. So there's your 1/2 mv squared. We've got 500 newtons for 6 meters, and that's going to give us a new 1/2 mv squared. And I will pause the video and just go run some numbers here to save us some time. So according to my calculator, there's the values. Do a little multiplying. Add the left-hand side. We get 5,400 equals 600 v squared. Divide both sides by 600. I think we're going to get something nice. I think that's v squared equals 9, which means v equals square root of 9. Make sure you get your 2 or 3 sig figs. 3.0 meters per second. There's your final velocity. So there's looking at a question where we've had an elf, a helper, that added some energy, and here it made the car go faster. Gave us some more kinetic energy. Let's look at one more example. Try to keep this video short. We'll just do one more. Let's talk about taking energy away with some work out. So this car, just to really quickly walk you through what's going on, I wish they did this here for 16-year-olds like you guys. This is a car where they've put training wheels, I say that in air quotes, on the car. That's actually lifting the car up a little bit, which reduces the normal force, which is reducing the friction force. So what's cool is this person in the vehicle right now is doing winter driving training. They're simulating being on a slippery surface by reducing the force of friction. So that'd be something super cool, I think, to have here, right? Is to practice your winter driving, practice driving on like snow, ice, slippery conditions in the middle of the summer. If you could put training wheels on a little car like that. Let's try this out. So we're going to find the distance the car skids. The initial velocity is 16.5 meters per second. Oh, in fact, actually, if you want, you could probably just cherry pick the numbers. You don't even have to write the words. The mass is 1,200 kilograms, and the force of friction is 2,800 newtons. We have seen questions like this in Chapter 5. The skidding car was a pretty classic example, and if you did all of your practice, you probably looked at questions like this about 4 or 5 times. You did them at least. Let's look at this question now in terms of conservation of energy. The skidding car example. So I'm going to go ahead and take a few seconds and list the whole equation and then go through that process of elimination because it's easier. So let's see what stays and what goes. Does this car start in the air / on a building / on a hill? No. Does this car start with some velocity? Well, it looks like the initial velocity is 16.5, so the answer is yes, that stays. Do we have a helper, an elf? Is there Joe pushing forwards on this car? You can look and say, no, there's nobody pushing forwards. I know the car's moving forwards, but nobody's pushing it forward, so that's out. Here the car is going to skid, let's assume to a stop. Does the car skid into the air / up a hill / up onto a building? No. We can assume the road's flat. If we skid to a stop, then the car is not moving at the end. But is there something pushing backwards on that car? Yeah, force of friction, heat. So what we're left with is kinetic energy of a car. When you hit the brakes and you come to a stop, all of that kinetic energy turns into heat. And if you've ever watched like race cars, maybe on TV or in person, you know that the brakes are what provide that friction force, and they get really hot, and sometimes they get so hot they actually glow orange. Or you can start to smell them sometimes too if you're following somebody down a hill and they're riding their brakes too long. That's just the heat. They're actually sort of melting the brake pads. So here we can't cancel masses because it only shows up on that left-hand side. It's not on the right-hand side, but we're simply going to plug the numbers in now. 1/2 times 1200. The thing started at 16.5. Don't forget to square that. The force of friction, they just give it to us here. We don't even have to find it. It's 2800 newtons times D. And that's going to be like a one-shot deal on the calculator, which is kind of cool. 0.5 times 1200 times 16.5 squared. So there's your kinetic energy, and then divide by 2,800. 58.3 m for meters. Done. Chapter 5, when we saw the skidding car examples, it was free body diagram, F net equals ma, and then kinematics. It was sort of a 3-part question. This is 1-part question. So it's a little bit more efficient, sorry, bad pun. It's a little bit quicker to get to the answer than it was to run F net equals ma. So try out box number 4 homework. This is a busy box. You'll see that there's lots going on. But it's really important that you try it out. You will notice, hopefully, that the second half of the chapter, the homework really drops right off. So we've kind of front-loaded the homework in this chapter. But this box will be really important. This is another big topic that shows up in Physics 12. You'll spend a bunch of time on it. So make sure this conservation of energy is something that you can wrap your head around and you get yourself pretty darn good at it. Any questions? Which you're probably going to have about this lesson, to be honest. Some of the questions in here are just weird in terms of how they set up, and I'd love to go over them with you in Zoom. So I'm going to say join me for a Zoom meeting, because there will be a handful of questions that I do with you. They're ones that right now, if we were in class, I would say, hey, let's start with these questions, but I don't want this video to get too long. So join me in a Zoom meeting. I've got a handful of the questions from the homework I want to do with you, ones that typically students get stuck with just because they're worded kind of weird or weirdly. So please hit me up in the next Zoom meeting. Let's chat physics. Let's get this all sorted out. You're welcome to email me as well. So hopefully we'll chat soon, folks.